Hello and welcome to this pre-lab video for the reaction spontaneity lab. The primary material out of this lab comes from a theoretical understanding, at least, of the concepts in chapter 12. That is a theoretical and conceptual understanding of the concept of entropy and a theoretical concept of Gibbs free energy and the relationships between all of those variables and each other. So this lab is actually very short and it's very concept focused. So thinking about things in big picture, qualitative, non-numeric terms, as opposed to the more quantitative kinds of ways. So let's kind of get an idea for where it is that this comes from, and that should help us a little bit to understand what it is we'll be asked to do. So we need to start with the idea of spontaneity. And for spontaneous reactions, again, thus far, our only real reference for spontaneity has been enthalpy. That is the heat of reaction. And we know that generally speaking, when the heat of reaction is negative, when it is an exothermic reaction, we know for a fact that a lot of those are spontaneous reactions. But the problem is, we also know of a number of reactions that are endothermic and also spontaneous. Now, one important thing to recognize here, one important thing to note, is that the term spontaneous, again here, means reacts without interference. So when we describe a reaction as being spontaneous, what that means is that that reaction is going to happen without any input of energy on our part. True, it might require just a little bit of energy to kickstart the reaction. We call that activation energy. But once we do, we'll see that there's a net energy loss by the reaction system. And so often that net loss comes in the form of heat energy. And those are what we call exothermic reactions. But we also understand that exothermic reactions are not the only kinds of spontaneous reactions. Think about a number of reactions that occur in solution. Think about cold pack, for example. That dissolution is a spontaneous reaction, but it draws heat into the system and away from the surroundings. It's endothermic. So because we can't just look at enthalpy, we are going to need to determine other criteria to help us to figure out whether or not something is spontaneous or non-spontaneous. And one of those criteria is something called entropy. Entropy is given here by the letter S, and it determines the extent of randomness or disorder in a reaction system. So the more disorganized the system becomes, the more entropy it has. Now, there's another definition out there that I kind of like, and it's about the idea of distributing energy. The more ways that we can distribute energy among the particles of a system, the more disorganized it is, the more entropy it has. Now, like enthalpy, entropy change, which would be delta S, is a process that is path independent and therefore a state function. And so this brings us to the second law of thermodynamics. Second law of thermodynamics tells us that for any irreversible process, that is any spontaneous process in the forward direction, there's going to be an increase in entropy of the universe. If the process is reversible, then that means that the entropy that is going this way would be matched by entropy change going that way. And so the net effect is zero on that entropy. But if we have an irreversible process and it is spontaneous, then delta S of the universe is going to be increasing, positive. And if it's a non-spontaneous process, then the entropy of the universe instead would be negative. So the entropy of the universe is always increasing when we have spontaneous processes taking place. That's the ultimate goal, and that's the ultimate concept that the second law of thermodynamics is trying to make. Now, we can focus on entropy on the molecular scale, and that's where this gentleman comes in. This is Ludwig Boltzmann, and he was able to describe and quantify the entropy of a system based upon this idea W. W standing in for what are called microstates. And those are unique arrangements of molecules in the system. The relationship here is logarithmic. And so basically, the more microstates there are, the more entropy there's going to be. And so we'll talk about microstates and kind of focus on that at a later time. I just wanted to kind of introduce the idea here, because what it ultimately leads to is, if we have more disorder, if we have more of these unique arrangements, we're going to get greater entropy. And we know that if we have a greater entropy and a greater entropy change, then we're going to see a spontaneous process taking place. And so when it comes to these microstates, we have to kind of break down molecular motion. And so there are 3 different types of molecular motion. We have focused primarily on this first one anytime we've talked about molecular motion: translational motion, the motion of a molecule moving around in its space in straight line motion. But there are also vibrational and rotational states as well. And the best way to kind of think about these is if we think about and change the way that we view bonds. If we think about bonds kind of like springs, instead of these rigid ball and sticks, what we'll see is that these springs can expand and contract, and that will create these different vibrational modes. And so the more bonds that we have in a molecule, the more vibrational modes it would have, the greater its entropy would be. We also talk about molecular motion in terms of rotation. So looking at this water molecule, can this water molecule rotate around this axis and spin around in a circle? And the answer is yes. And so obviously, the more complicated the molecule is, the more rotational variation is going to exist. And so all of these translate to more microstates. The more ways that we can express translational, vibrational, and rotational motion, the more microstates we are going to introduce for a particular molecule, and therefore the more entropy it's going to have. And so Boltzmann's idea, and where the Boltzmann equation ultimately comes in, is, can I look at a particular snapshot? If I took a look at the molecular structure of a substance at a particular given time, and I took a picture of what it was at that time, how many different pictures would I create before I created a duplicate of one of my previous pictures? That's what the microstates are. And so the more unique pictures I have of the molecules, the more unique microstates I have. And so entropy on the molecular scale This is slightly different than the equation that we saw on Boltzmann's tombstone, but the idea is essentially the same. We've got a logarithmic relationship between microstates W and entropy S. The two are related by K, the Boltzmann constant, which is 1.38 times 10 to the negative 23rd joules per Kelvin. Now, knowing the entropy of a given system is somewhat useful, but we really are more interested in processes and reactions. So we have to evaluate changes in temperature, changes in reaction state. And so delta S can be expressed as this difference in the Boltzmann values, which if you know your logarithmic rules, we know that we can turn the subtraction into a fraction here, and that delta S is ultimately going to be related to this fraction. And so what does that mean? Well, if my final number of microstates is greater than my initial, then the logarithmic is positive, and so is delta S. But if my final number of states is fewer than my initial number of states, then my natural log term is going to be negative, and my delta S is going to be negative as well. So the more microstates are created, the more our entropy change is going to be positive. And so this kind of provides us that second piece of the puzzle. And so just looking at it further, what we can see is that, okay, if we look at the number of microstates, we can see that there will be increases in microstates and therefore increases in temperature or in entropy when we see increases in temperature. So as delta T increases, delta S generally increases as well. Changes in volume, we're going to increase the amount of space. So that means that there's going to be more room for those molecules to move around in, more microstates created as a result. So with increases in volume, we will also see increases in entropy change and the number of independently moving molecules. As our number of moles changes, so will our delta S. So those are the things that we kind of want to think about as we're going through this experiment is, what are some things that are going on? What are some things that are happening that we can observe and use to predict? So what are some of the big picture implications of entropy? Well, first of all, if we look at it from a phase of matter standpoint, solids are the most ordered because of the closeness of those molecules to each other, the organization of those molecules, the fact that they form these crystalline, rigid structures. They are highly ordered and have low entropies as a result. Gases are far apart from each other. The particles are moving around very quickly, and there's usually a lot of them. They have the most inherent disorder, and therefore the largest entropies. And then liquids are kind of somewhere in the middle. Now, liquids do tend to shade more toward the solid side than the gas side, just because there's a lot less freedom of movement. But there is kind of an in-between here, because they are not nearly as ordered in terms of their organization. They don't form crystalline structures. They are a little bit more loose, a little bit more disorganized as a result. And so one of the things that you should be able to do is, just by looking at chemical equations, you should be able to predict what kind of entropy change you would expect. So for example, in this problem, we are going from water in the liquid phase to water in the gas phase. Well, we already know that gases have greater entropy than liquids, So we should expect that delta S is going to be positive in this case. Now, what about this second one? In this second one, we have ions that are in the aqueous phase. They're dissolved in water, and they're turning into a solid. Well, solids are the most ordered. They have the least entropy. Aqueous solutions are not terribly ordered, but we do have a high variety of molecules there. That's going to give it some disorder. So we've got higher entropy in the reactant side, lower in the product side. We're going to get a negative delta S as a result. In this third one, I've got a solid with low entropy reacting with a gas that has high entropy to make a solid with low entropy. The net effect here, we've got a high entropy substance turning into a low entropy substance. Delta S should be negative here as well. In this last one, I've got two gas molecules, nitrogen and oxygen, turning into two other gas molecules of nitrogen monoxide. The change in delta S, that one we can't really predict just by looking at the chemical equation. For that, we need to use the standard molar entropy values, which are found in most reference texts. And very similar to how you did heats of formation with enthalpy, you would do the same thing with those standard molar entropies to figure out the value. Can't really predict it other ways, though. So entropy gives us a good base for the story as well. The problem is entropy is like enthalpy in the sense that it only tells one part of the story. More often than not, we're looking at the entropy of the system and not necessarily the entropy of the universe. And so there are conditions, there are places where we will see substances that have negative entropies, like this one. This is a reaction we've seen many times, the precipitation of silver chloride from solution. We know this reaction is spontaneous. You put a silver solution with a chloride solution, you're going to get a solid. But it's spontaneous, yet it is negative in its entropy value. Why? That's because we don't have the full story. What we need to do is we need to put something that puts them all together. And so the Gibbs Free Energy allows us to make that kind of determination. What Gibbs Free Energy does is it looks at the total energy of the system, not just the enthalpy for the heat, not just the disorder for entropy, not just what temperature it is. It puts them all together. And the relationship is this: the change in free energy is equal to the change in enthalpy minus the temperature times the change in entropy. Now, keep in mind, this is an energy calculation. We need that temperature to be in Kelvin. One other thing that is important to note: enthalpy is usually reported in kilojoules per mole. Entropy is usually reported in joules per mole Kelvin. So if I were going to calculate this quantitatively, I would need to resolve this unit mismatch before I do the subtraction. If we're at standard conditions, then yes, delta G, delta H, and delta S all have standard forms, and we could calculate them in the same manner. Since we are now looking at the total amount of energy, now we can evaluate positive and negative and use it to determine spontaneity completely, not partially like enthalpy or partially like entropy, but wholly and completely. If the free energy is positive, that means that net energy is flowing into the system. That is non-spontaneous. If delta G is negative, that means that the reaction is releasing energy in net to the surroundings. That is a good thing. That is a spontaneous reaction. If delta G is 0, there is no net energy change. The system is at equilibrium. And remember, equilibrium is just another way of saying we've got a reversible reaction. Temperature does play a significant role into this, because what we can see is that there are certain scenarios where we are going to have always spontaneous conditions. There are scenarios where we are going to have negative or never spontaneous conditions. And so you can see that if enthalpy and entropy are both favorable, we're going to get a spontaneous reaction. If enthalpy and entropy are not favorable, we're going to get a non-spontaneous reaction. Where it gets difficult for us are these conditions. What if the sign for enthalpy and entropy is the same? Well, then we call these temperature-dependent reactions. And that temperature dependence will yield spontaneous conditions at certain temperature conditions and non-spontaneous conditions at other temperature conditions. It is going to vary completely by temperature. So let's move on then to the next part of this, and that's how do we go from these kind of concepts to looking at our prelab. And so we're going to switch over to the prelab here. And so if you look at the prelab, you'll see that the questions here, a couple of them come from the introduction section. So if you go to the discussion here, you get information about what we were just talking about. You'll also need to have information about a hydrate, because you're going to be working with hydrates. And hydrates are really pretty simple. They're just substances that have water molecules trapped inside of their crystals. And that will become important when trying to evaluate exactly what's going on in one of the reactions that we're going to view. But I want to look at number 3 here just as an example, because you can see that most of these other ones are talking about spontaneity, exactly what we were just looking at in the PowerPoint. I want to look at this one in particular just because it's first here, and if you can kind of get this one, you can get the rest of them as well. So let's consider the vaporization of water at 110 degrees Celsius. So we're talking about water going from the liquid phase to the gas phase. What wants to know is what are the signs for the heat of vaporization, the entropy of vaporization, and the free energy of vaporization at this temperature. Now, we could go and look all these values up or calculate them, but we really don't need to. We can just evaluate them based on where they are. So, logically speaking, to turn water from a liquid to a gas, are we going to have to enter and put in energy or take energy away? And the answer should be pretty obvious to you. To get this to vaporize, we know that we're going to have to input energy. Inputting energy is going to be endothermic, so the heat of vaporization would be positive as a result. As far as entropy goes, we have our equation And we can see from this equation, we're going from a more ordered state as a liquid to a less ordered state as a gas. So our entropy of vaporization should be positive as well. So now we have to look at, we've got a positive enthalpy and a positive entropy. If we go back to that table, we're here in the bottom row, and it says, okay, this is temperature dependence. It could be positive or negative for delta G. In particular, these are the kinds of reactions that at high temperatures are spontaneous and low temperatures are non-spontaneous. Question is, which does this actually qualify as? And the truth is, the word low temperature or high temperature is relative. It's dependent on what the equilibrium point is. What we do have as far as information goes, however, is we do have this little bit about temperature, 110 degrees Celsius. Now we know that the boiling point of water is 100 degrees Celsius. That would represent equilibrium, which would indicate delta G being equal to 0. This is above that. And so there's our answer. Would this vaporization be considered spontaneous at this temperature? Absolutely. And this would make sense to us, right? We know that if water is going to boil at 100 degrees, it certainly is going to boil at 110 degrees as well. The reaction is now spontaneous instead of at equilibrium. And anyone who's heated up a pot of water knows that's exactly true. So what you need to do for the remainder of the pre-lab here is just this. Evaluate. You've got a positive value here and a positive value here. What does that mean? We'll go to the chart. Go to the chart, figure out when is it going to be spontaneous at every temperature. When is it never going to be spontaneous? This chart here is going to give you that information. Again, this is table 19.3, but that's not table 19.3 in your textbook. Remember, all this stuff is out of chapter 12. That particular chapter, this particular table would be found in chapter 12 as well. And it is, pulling up the book here, it is table 12.4, which is on page 574 of your textbook. So that is where you would want to look if you're looking at your textbook for the information that we're interested in. So that's where I'm going to close this particular video, is right here. Certainly, if you have questions about the pre-lab and about the material as you're coming through and going into the pre-lab, getting ready for this experiment, please feel free to reach out to me and I'll help you out as best as I can. But that's it for now. So take care, and I will see you next time in lab.